Okay, good morning. This is David J. De Los Reyes. My topic for tonight will be it's on advanced mathematics. This is now lesson number 17. And this deals with Laplace transform. Okay, I will check my camera. Oh, it's fine. My lesson for tonight or for this morning is actually March 8. It's around 2 a.m. in the morning. My lesson for this morning will be Advanced Mathematics, lesson number 17. And the subject matter is very interesting. This is one of the interesting topics on Advanced Mathematics. It's Laplace Transform. Okay, so before we could proceed with problems on Laplace Transform, let's try to bring out the so-called transformation table. That is the transformation from a function of t to a function of s. That's why it is Laplace. Originally, under the so-called differential equation solution, we are under function of t. But if we are to solve problems, okay, on circuit analysis, we must have to transform this function of t to a function of s. That's why it is so-called Laplace transform. And for this morning, I will be discussing the first three formulas, transformation formulas. That is the transformation of 1, okay? The transformation of this to Laplace is actually 1 over s. And for B sub O, meaning initial voltage 0, B sub O, that will be B sub 0 s under Laplace. And the third one, for this morning, I will just only discuss 3, so we could accommodate all the 3 for the discussion, okay? That is e raised to a times t. The transformation of this and Laplace is actually 1 over the difference s minus a. So it's a must that we must have to memorize these 3 transformation formulas. 1 is 1 over s, B sub O is B sub O over s under Fs, and e raised to alpha t will be 1 over s minus a. Under differential equation, we are under function of t, and under Laplace, we are under capital letter F as a function of s. We will transform all those function of t to a function of s. Then we will try to manipulate or algebraically manipulate the equation. Then we will try to go back on the so-called inverse Laplace so we could bring out the final solution. Okay, let's try to bring out the derivation of the formulas. Okay, number 1. I will try to derive the relation of 1 and 1 over s. That is a transformation from function of t to function of s. That's why we must have to use Laplace transform. The Laplace transform, this is like a capital letter L. It emanates from Laplace. This is L, or Laplace, meaning if we try to read this one, Laplace transform of 1 should be equal to, okay? From the previous discussion, it is actually the Laplace transform of anything is actually equal to, what do you call this? We will take the original thing times dt, then we will multiply this by e raised to minus st, okay? But with the initial limit 0 to infinity. If we try to take the Laplace transform of anything, it will be that given function times dt times the exponential thing e raised to a to the minus st with the limit from 0 to infinity. That is the general formula for Laplace. If we would like to bring out the transformation. So the Laplace transform of 1 should be equal to the integral from 0 to infinity. The given term is actually 1, so this is 1 times dt times the value e raised to minus st. That is a standard formula for Laplace transformation. if you try to bring out the transformation of anything to Laplace. So if we try to integrate this one, this should be equal to 1 times dt is just dt. So if we try to simplify this one, it will just be simply the integral from 0 to infinity of e raised to minus st dt. It is an exponential function. Okay, let's try to bring out the so-called verification of the exponent. The exponent is actually minus st. And I place it here, s is constant. T is variable. Okay? So if we will try to take the differential of both sides, the differential of u will be du, the differential of the right hand side, constant, times the variable function, so that it will be minus s times the differential of time, which is dt. So du supposed to be is actually minus s dt. Okay? It is not exact. Because if it is exact, we could now integrate the right hand side to be under the so-called exponential function. And to integrate it as an exponential function, we must have to introduce negative 1 over s before. Okay? So I place it here, negative 1 over s, the integral from 0 to infinity of the given exponential function times the complete differential. The complete differential supposed to be is minus s dt. So after placing minus s dt over here, then we compensate for that negative s by placing negative 1 over s here. This now falls under the exponential function. So what will come out will be negative 1 over s times, it is just simply the integral of e to du. Of e to du is actually e to du. Okay? We verified the complete exact value of d already. So what will come out will just be simply e raised to minus st with the limit from 0 to infinity. Okay? We are now on the so-called definite integral. We got a limit, lower limit, upper limit. So we pass by integral calculus. That's why one of the prerequisite of advanced mathematics is integral. So this is now negative 1 over s. Applying the upper limit, this should be e raised to negative infinity. S times infinity will be negative infinity minus the value of the lower limit when we apply t to be 0. So that this should become e raised to s times 0 will be 0, so this will be 0. Okay? And e raised to negative infinity will be 0. Because if we try to simplify this one, e raised to negative infinity can be written as loads of exponent, guys. 1 over e raised to infinity. So this should be 1 over 2.72 something to raise to a very, very big number should be a very big number. And 1 over very big number should be 0. So the upper limit is actually 0. Minus, this is e to the 0, and e to the 0 is actually 1. So this is 1. Okay? That is just an application of the upper and, what do you call this, upper and lower limit. I will erase this one so it will look nice. So what will come out now? This should be negative 1 over s times open quantity e to the negative infinity 0, e to the 0 is minus 1. This is minus minus, so it will now become plus. This is over s. So formula number 1 under Laplace transform is that the Laplace transform of any number 1 should be equal to just simply 1 over s. It is this. Okay? Function of t, function of s, the equivalent of 1 under function of s is actually 1 over s. And the proof is this. Okay? So memorize this by heart. Because when we go to the so-called application problem, think about the Laplace transform of 1 to be just simply 1 over s. It's not hard. Okay, that's number 1. Okay, let's proceed with number 2. the Laplace transform of B sub O, meaning the B here is voltage, 0 here is initial, meaning the initial voltage. The Laplace, because this refers to circuit analysis, okay? The main concentration of the solution of Laplace transform is on the so-called circuit analysis, transient problems. The Laplace transform of B sub O should be equal to the same. How we will follow this? The integral from 0 to infinity. What is the given function of t? It is B sub O times dt times e raised to minus st. This is the standard formula for taking the Laplace transform. Okay? We just replace originally 1 by B sub O because we are now under formula number 2. Okay? So this should now be equal to B sub O here, I place it here, is constant. Okay? So if we try to integrate the right hand side, all constants should come out. So this should now be B sub 0, the integral from 0 to infinity of e raised to minus st dt. Okay, let's try to verify the differential of the exponent. The exponent is minus st, right? And the differential should be minus s dt, and it is not exact. So to integrate the right hand side, for it to fall under e to the u, we must have to introduce outside the the reciprocal of negative s. And the reciprocal is actually negative 1 over s. This is times B sub O. The integral from 0 to infinity of e raised to minus st, the complete exact differential supposed to be is minus s dt. Okay? After placing this as a negative s dt and placing outside negative 1 over s, this now falls under the integral of e to the u du, and it will just be simply e to the u, right? So this will now be B sub O times negative 1 will be negative B sub O over s, open bracket, the integral of this, it falls under e to the u, so this will be e raised to minus st, close bracket, with the limit from 0 to infinity. Simplifying this one, this will be negative B sub O over s. Applying the upper limit, we put time to be infinity. S times infinity will still be negative infinity, a very small number, minus, when time t is 0, s times 0 will be 0, so this will become 0. And e raised to negative infinity, as 1 over, hold on. E raised to negative infinity is actually equal to 1 over, laws of exponent, the one you are doing on short views. This will be e raised to infinity. So this should be 1 over e raised to 2.72 raised to a very, very big number is just a very big number. Okay, so this is a very big number. And 1 over a very big number, this is almost 0. So this is 0. Okay? Laws of exponent. That's why the short videos on the short speed, we are using it here. So e raised to negative infinity is 0, e raised to 0 is 1, so what will come out will be negative b sub 0 over s times the quantity 0 minus 1. A minus 1 times negative b sub 0 will be positive. This is now positive, all over s. So under the so-called transformation formula number 2, the Laplace transform of b sub O is just simply b sub O over s. It is this. Okay? The Laplace transform of b sub O from function of t to function of s is just simply b sub O over s. Memorize this by heart. Because when we go to the application problems, okay, just recall this one. It's just like in the so-called integral calculus. If we have memorized around 100 formulas just to integrate anything under integral calculus, under Laplace transform it is only 1 to 13. So it is much more easier than integral calculus. This is just formula number 2. And the derivation is this. And the final formula is this. The Laplace transform of b sub O is actually b sub O over s. Laplace of b sub O is b sub O over s. Okay, let's proceed with number 3. I will check my calendar again. For number 3, the transformation of e raised to at in Laplace is actually 1 over s minus a. Okay? We have encountered this equation here under the transient problem, right? So the equivalent of this under Laplace is 1 over s minus a. Okay, let's proceed with the so-called derivation. The Laplace transform of e raised to a times time should be equal to the integral from 0 to infinity. The given left-hand side is e raised to at times dt times e raised to minus st. Okay? Simplifying this one, this should be equal to the integral from 0 to infinity. I go on the right-hand side. E raised to at times e raised to minus st closed quantity dt. And actually, we could simplify this one. Again, laws of exponent, same base, okay, different exponent. So this compressed equivalent of this will be same base plus the sum of the exponent plus negative thing plus open quantity negative st will be, we are taking the sum. So there's a common factor t, so same base now raised to the difference a minus s closed quantity t times dt. Okay, it still falls under the so-called exponential function. Let's try to verify the so-called validity of the differential of the exponent. The value of the exponent is actually the value a minus s times t, and du will be a minus s times dt. I place it here, a and s are constants. So if we try to take the differential of this, a minus s is still a constant, so it will be a minus s times the differential of time. So a minus s times differential of time. And unluckily, it is not exact. Okay? It is not exact. We lack the term a minus s over here. Okay? So for the right-hand side to be integrable, we will introduce the reciprocal of this outside, then we will maintain the exact differential inside a minus s times differential of time. Okay, this should be the exact differential. We introduce this one, so this is now under the integral of a to the u. So this is 1 over a minus s times, open bracket, a raised to the difference a minus s times time with the limit from 0 to infinity. So this is 1 over a minus s, a raised to a minus s times 0, infinity, minus e raised to a minus s times 0. If a is not equal to s, and s is greater than a, okay, if we try to simplify this one, it will just be simply a raised to negative infinity. And a minus s times 0, this will be 0. So the power of the lower limit will be 0. And if we try to simplify the first one, the upper limit, this is 0. A raised to negative infinity. So 1 over a minus s times the quantity 0. A raised to 0 is 1, so this is minus 1. Okay? And if we try to simplify the final Laplace transform of a raised to at, this s now will now be plus because this is negative 1. And this a here times negative 1 will be, okay, minus a. So what will come out will be the Laplace transform of a raised to at will be equal to 1 over s minus a. And this formula here is this relation here. That is the third transformation formulas for Laplace transform. That is, the Laplace transform of e raised to at should be the ratio 1 over s minus a. Oh, that's it for this morning. I brought out the three formulas I brought out the so-called derivation, so the next time around, we will discuss again 3. After discussing all the 13 formulas, we'll go to the so-called application problems, because I think it is much more easier to solve problems if we know how those formulas was, what you call this, derived. Okay, I will check my camera again. Okay. So, for those who are studying advanced mathematics, this is for you guys, okay? If you would like to subscribe to my channel is at youtube.com/@prof.david.j.de. And if you want to share it, please click share. Okay, this is now my 3rd subject matter that contains long form videos. Okay, it's a complete lecture. So actually, I've got the differential calculus, integral calculus, differential equation, and this is now the 4th one. I am now completing this advanced mathematics. It is a long form video. So for those who are taking engineering and you are studying advanced mathematics, this is for you guys. Okay, good morning from Los Angeles.